All right, this video is about a related rates problem, and the problem is the one you see in the upper left corner of your screen. A baseball diamond is a square with sides of length 90 feet. A runner sprints from home plate to first base at a constant speed of 16 feet per second, while a fielder at third base prepares to throw the ball to first. At the moment when the runner is 1/3 of the way from home plate to first, how fast is the distance between the fielder and the runner changing, and is it increasing or decreasing? All right, so the first step in solving any related rates problem, in my opinion, is to make sense of the problem, figure out what's going on, and draw a picture. The picture is kind of mandatory in most cases. At least in anything that involves geometry, we certainly want to have a good picture. So let's draw a baseball diamond. It'll look kind of like this. This should be a square. Drawing a square diagonally for me apparently is very hard, but that's my best attempt. And really, you don't have to have a great square. You just have to have something that can convince you that it's a square. So this has right angles all around. Okay, those are not the bases. I'm making markings to show those are right angles. And then for those not familiar with the game, this is home plate. This is first. This is second. And this is third base. And in this problem, we have a runner who is on the path from home plate to first base. So maybe somewhere around here. We are talking about the moment when the runner is 1/3 of the way from home to first. So that's why I put the runner there in the picture. But one thing we have to keep in mind is that that is something that's varying, how far the runner is from home or how far the runner is from first base. But anyway, the runner is going to be moving in this direction. That's just a reminder to us. Okay, so the next thing that we have to do once we've made sense of what's happening in this problem is we have to be really clear about what it is we know and what we're looking for, especially what we're looking for. So the question is, how fast is the distance between the fielder and the runner changing? And where is the fielder? The fielder is at third base. So I'm going to draw a little fielder there. Fielder plays for the other team. And then the distance between the fielder and the runner can be represented as the length of this line here. So if the runner's right there, then I've got a little line there that shows how far it is from the fielder to the runner. Now, if you look at that line, let me just go ahead and fill that in. So we have a solid side of a figure there. You'll notice that that is the hypotenuse of a right triangle, the right triangle consisting of this side, and this side. We know that's a right angle there. So we have a triangle, and the distance between fielder and runner is the hypotenuse of that triangle. That's going to be something that's useful to know in this problem. So one thing I want to do is write down names for anything in this problem that is varying and that is important to our solution to this problem. Certainly the distance between the runner and the fielder is going to be one of those things. I'm going to call that, just because I don't like calling variables in these related rates problems D, I'm going to call that Z. And then we want dz over dt. That's the rate of change of z, or the distance with respect to time. What other quantities are important to us in this problem besides that distance? Well, we know that the runner is on their way from home plate to first, and the distance that they are from home plate is one of the sides of this right triangle. That makes this something that we might want to keep track of. Figuring out what quantities you want to keep track of is really as much instinct that you develop over time as much as anything else. But it seems like this distance x, distance from runner to first, or sorry, runner to home, seems like something we might want to keep track of. And then another distance in this triangle that seems important is the other leg of this right triangle, which is 90 feet. Because that is 90 feet, and the length of that base path never changes, we might as well just call it 90 feet. We could assign that another variable name. We could call it y, for example. But I'm really not going to use that as a variable in this problem. It's not going to vary. It's always 90 feet. So I'm best off just leaving it as such, leaving it as 90 feet. All right, so I now have x, z, and the other side of the triangle has length 90 feet. So now I want to start writing down any relationships that seem pertinent among the variables I've defined. I could keep identifying other variables, like I could say, well, maybe the distance from the runner to second, or maybe the distance from the runner to first. And those might seem like they are varying degrees of relevance. But in this problem, it feels like this is extremely relevant and this is extremely relevant. So I'm going to try writing down some relationships and see if those give me enough ammo to solve the problem. So let's see if that works. All right, so because I have a right triangle here, by the Pythagorean theorem, I know that x squared plus 90 squared is equal to z squared. Anytime you have a geometry problem or a problem that seems to involve geometry, a good practice is to look for right triangles. And then once you have those right triangles, you're going to use some combination of the Pythagorean theorem or right triangle ratios like sine and cosine, or something else like possibly the area of a right triangle. It depends on the problem that you're working on. But in this case, the Pythagorean theorem is exactly what we want because we know some things or we're interested in the relationship among these three side lengths. All right, so by the Pythagorean theorem, I have x squared plus 90 squared equals z squared. And at this point, because I'm interested in finding dz dt, the rate of change of the distance with respect to time, I'm going to take the derivative of both sides of this equation because I know that each side of this equation represents a function of time, and they represent exactly the same function of time, which means their derivatives have to be exactly the same as well. So taking the derivative of the right side with respect to time, I get 2z times dz dt. And that again is because I can really think of this as some function z of t squared, because z is really a function of time. And then the derivative of that, when I take the derivative with respect to t, I get 2 times z of t, that's by differentiating the outside function, which is squaring, times the derivative of the inside function, which is z prime of t. All right, so my derivative on the right side is 2z times dz dt. On the left side, I get 2x dx dt plus, and then this is the advantage of calling this 90 squared rather than a variable squared, because 90 isn't changing, its derivative is 0. And now I have that 2x dx dt equals 2z dz dt. The thing I want to find is dz dt. So let's take stock of what we know. We have at this moment a value for x because we were told that we want to analyze the moment when the runner is 1/3 of the way from home to first. So at this moment, x is equal to 30 feet because we are 1/3 of the way from home to first. And then what about dx dt? Dx dt we know is a constant. We know that the runner is moving at a constant speed of 16 feet per second. So dx dt is 16 feet per second. And it's not incorrect to just write x equals 30 and dx dt equals 16, but it might be helpful for us to just keep track of the units here, 16 feet per second, and then 30 feet. So I know both of the quantities on the left-hand side. I know x, I know dx dt. I want to find dz dt, but now what's left is I need to figure out what z is. If I can't figure out what z is, I'm going to be stuck because I'm going to have two unknowns in this equation. Well, what is z at this particular time? I know what x is. X was 30, and I know that the length of this other side was 90. So I can use this relationship, the Pythagorean theorem, to figure out what z is. So since x squared plus 90 squared equals z squared, I know that at this time, 30 squared plus 90 squared is going to equal z squared. So z squared is 900 plus 8100, which is 9,000. So z is going to be the square root, the positive square root, since it's a distance, of 9,000, which comes out to, according to my calculator, 94.86, 868. So let's call that 94.87. All right, so let's move this up. Just create a little bit more room to finish this off. All right, so at this point, I think I have all the ingredients I need to solve this problem. So since 2x dx dt equals 2z dz dt, and at any time I could go ahead and just cancel off those factors of 2 that are on both the left and right. I just haven't thought of doing that yet. So I guess I'll just leave them there. We have 2 times 30 times 16 equals 2 times z, which was 94.87, times dz dt. So solving for dz dt, we get dz dt equals, And at this point, I think I will cancel those factors of 2. I just get 30 times 16 over 94.87. And what does that come out to? Let's use our calculator. 30 times 16 over 94.87, I get 5.06, almost exactly, 5.06. All right, now at the end of this problem, we need to make sure and figure out what we've got, understand what it means, which means giving it appropriate units, and make sure we've answered the question, because the question wasn't just, what is dz/dt? It was a little bit more than that. It was, how fast is the distance changing? We now know the answer to that. It's changing at a rate of 5.06 feet per second. But also we were asked, is the distance increasing or decreasing? Well, all of this work that we did led us to a point where we have dz/dt equal to a positive number. And we should make sure that there's nothing that we did that would have entailed a negative sign, like make sure that we got dx/dt exactly right, for example. But we know that that was correct to have that as a positive 16, because x is increasing as the runner moves from home to first. So this really is a positive number here, which means that my distance is increasing. And that passes the common sense test as well, because if the fielder stays here and the runner's moving this way, this triangle gets bigger and the hypotenuse gets a little bit bigger as the runner progresses. So that's it. So that now we know that the distance was increasing at a rate of 5.06 feet per second.